We're going to be using ODS Pro and some scripting, and I've breadboarded a lot of what we're going to talk about today using the scripting that's a standard part of MEscope. Those of you that own it probably haven't tried it or used it much yet, but it's a great way to automate and to prototype some calculations that you may want to try out with your data that aren't available in the MEscope commands. Let me bring up some slides first, and I'll start off with them, and we'll just talk about what we're going to do here today, and it's a lot of material. We're probably going to repeat this webinar next month where we do impact testing, or as I'll show you here, we simulate a lot of it. Vibrant's a software company. We're not a consulting company, so we rely on customers like you to go out in the real world with MEscope and try some of this out on real data. So I'm going to show you some simulated results today, and then next month we'll do the impact testing using this same idea of using transmissibility. So this is kind of a, you can see here the opening. This is a technical paper that we are preparing for the IMAC. That's the International Modal Analysis Conference. It's coming up in February next year, and the title is ODS and Modal Testing Using Transmissibilities. Now, normally we don't use transmissibilities. We use frequency response functions, or we use ODS FRFs, or we use cross-spectrum measurements. So we're going to talk about all these different types of measurements today and what's different about them. Let me scroll down here and, well, let me back up first and talk about the requirement here. This is not a finished slide, but let's just read the words. ODS and mode shapes require a single reference set of measurements. So that's what's unique about using MEscope to do ODS testing or modal testing. We need a single reference in the data. Now, by that we mean that one of the sensors remains fixed throughout the test. So that's what we talk about when we're doing a single reference test, either looking just at the ODS by putting a cursor in a set of cross spectra, FRFs, or something that's unique to MEscope called an ODS FRF. Experimental mode shapes down here are obtained by curve fitting, and again we need at least a single reference set of cross spectra or FRFs. Now, why would we measure one versus the other? Well, the cross spectra we curve fit when we can't measure forces. FRFs, we always have to measure the forces. So when we're measuring cross spectra to get experimental mode shapes, we call that OMA, or operating modal analysis, or output only modal analysis. There's a lot of different terms that are used to describe those. But here's the difficulty with single reference testing. If we're going to get ODS or mode shapes, we need a single reference set of measurements. Direct measurement of a single reference set of, again, I'm going to be repeating this, cross spectra, FRS or ODS FRFs, requires that one of the sensors remains fixed during the test. So that's what we mean by a single reference. One of the sensors has to remain fixed. That requirement can create a problem when we're testing any kind of a large machine, a piping system, a bridge, a building floor, anything like that. We have to run long wires from the reference sensor to the multi-channel acquisition system. So all of these measurements that we're making are called cross-channel measurements. In other words, we're measuring the vibration or response or input in the case of a force between one of the sensors and another sensor where we have simultaneously acquired the data. So we need at least a two-channel measurement to, or an acquisition system to make these types of measurements. Okay, here's a difference between an FRF and a transmissibility. Just a subtle difference. And some of you have measured transmissibilities, and you can post-process that data in MEscope. Here's the difference. An FRF is defined as the Fourier transform, or the Fourier, the FFT, of signal 2 divided by signal 1. So this is using the MEscope nomenclature where we do 2:1. What that means is that 2 is my roving sensor and 1 is my reference. So you can see that in this case, if the force, I'm testing with a shaker or I'm testing with a roving accelerometer, then the accelerometer is the roving, that's number 2, and the force is the reference, number 1. Transmissibility is the same calculation, FFT of 2/1, except it's a ratio of accelerations. So that's the only difference. And some of you have made these measurements. It's a common way to make measurements when you cannot measure the forces. So you're either testing something where the force is distributed, like a running machine, or you're driving a car around a test track, or you're flying an airplane, or whatever it is, and you want to measure, you want to do an OMA, then you're going to measure a ratio perhaps of accelerometers, or you're going to measure a cross spectrum between 2 accelerometers. So we'll get into some of the differences here as we go along. Okay, the difference between the FRF and the transmissibility. The FRF always is defined as having a force in the denominator. And that's the difference. The transmissibility is always a ratio of 2 accelerometers. So we're not measuring forces. There's the advantage of the transmissibility. We don't need to measure the force, even though we may be applying the force with an impact hammer or multiple shakers or a single shaker, things like that. Let's go down here a little further. Here are 2 properties that we're going to take advantage of with these transmissibilities. That is, if I multiply transmissibility 3, this is 3/2, times transmissibility with 2/1, I actually get the transmissibility of 3/1. So that's a property of a transfer function, and we can apply this to transmissibility. So the product property. The inverse of a transmissibility is basically we're inverting, so we're exchanging the numerator and the denominator. So if I've measured transmissibility 2/1, I can simply calculate transmissibility 1/2 by taking the inverse of 2/1. Very simple stuff. Transmissibility chain. This is what we're going to use here to make these measurements. It's something a little bit new. We've defined a new term here, but it's a very simple concept. I can measure a chain of transmissibilities with 2 accelerometer or 2 response sensors. If I use 2 uniaxial, then I only need a 2-channel analyzer to do it. I put an accelerometer signal into the 2 channels, simultaneously acquire the data, and I can form a transmissibility of 2/1. And you can see the chain down here. I can do 3/2, 4/3, 5/4, 6/5. So we're doing this in a sequence with a 2-channel analyzer. If I have triaxial accelerometers, and I have a 6-channel analyzer, then I can do it with triaxials. And if I have non-contacting, we can use a laser vibrometer or a photonic sensor, other types of non-contacting sensors. Again, we're just measuring the response, the vibration response of the structure as we go along. Here's a picture of what we're talking about here. And we're going to actually look at some data on this aluminum plate. I'm going to go along with 2 accelerometers and a 2-channel analyzer making these measurements. So you can see transmissibility 2/1 here is simply defining the first accelerometer as an input, so that it'll be a denominator term or a reference. The second accelerometer is the output, and again I'm using MEscope lingo here, input versus output. That's the way we form the transfer function or the transmissibility between 2 and 1. And then again here the orange ones is the transmissibility between 3 and 2. And so as I move along with a pair of accelerometers, I am measuring these transmissibilities as the structure vibrates. And over here is a force, but I don't need to measure it. It can be an impact, it can be a running machine. As I said, it could be a car going around a track. So we don't need to measure the forces. That's an advantage of what we're going to do here. Benefits of doing this transmissibility chain. Don't need to measure the forces. Only 2 sensors are needed. Variations in force levels are accounted for because of forming the ratio of the 2 accelerometers. And the transmissibility chain, and we're going to see this, can be seeded to obtain a single reference set of cross spectra, FRS, ODS, FRS. That's what we need to look at to animate an ODS from our data or to curve fit some FRS and get mode shapes. So this is the real advantage of doing things this way. So here's how I build a single reference chain of transmissibilities from a transmissibility chain where the reference keeps changing. Again, the reference being the denominator. So if I start out with transmissibility 2,1, I multiply that by transmissibility 3,2, which I've measured between points 3 and 2. I now have the transmissibility between 3 and 1. So you can see as we go through this recursive multiplication here, we're going to do this in a minute in MEscope, we can build a single reference set of transmissibilities. Then we're going to seed that transmissibility chain with, in this case, a cross spectrum or an FRF or an auto spectrum with linear. The difference here between what we're calling a cross spectrum and an auto spectrum is the auto spectrum is just a cross spectrum of a signal with itself. So a little bit of mathematics behind that, but hopefully most of you understand what I'm saying there. But here, if we have this chain now of transmissibilities with respect to 2 versus 1, 3 versus 2, 4 versus 3, as we showed in the picture that we've measured on the structure, and then we seed that with a cross spectrum between 0.4 and 0.20 here. 20 is a reference. It can be any point on the structure where I've measured a cross spectrum. So we just picked out a number of 20 here, but the important thing is that 4 is a response that's in this chain of transmissibilities. And now you can see that if I walk in one direction here from the seed location, I end up with the transmissibility at 1, or not the transmissibility, but the cross spectrum, cross power spectrum, 1 to 2 to 3, and 5 to 6. Now I got a set of data, a single reference set of data that I can use for ODS. And if I do it with FRS, same thing, I end up with a single reference set of FRS that I can curve fit and get the modes. Now, I'm going to move along quickly here because there's another thing we can do here, and we call it the Slinky Test. So we've already trademarked it, and people have already said, well, gee, what about the real Slinky? Well, most of you know what a real Slinky is. It's a coil of wire that'll walk down your stairs and so forth, and it's because one end kind of leaps over the other end as a Slinky walks down your stairway. I had one as a kid, maybe you have also, and it's still around. It's a very popular toy for kids. But here's what we're doing here. We're saving a lot of moves of the sensors, the accelerometers, by simply taking the first accelerometer and unattaching that from the structure and moving it over here to the 3rd position. Number 2 stays where it was, and we make the 2nd measurement. So the first measurement we make same as we did before. 2nd measurement, we move 1 over here. We don't have to change the wire to the analyzer. Now it's the input, So transmissibility 2.3 is now being formed instead of transmissibility 3.2. So we reverse the input and output here. Very easy to do in MEscope with our acquisition window. And you can see that as we do this Slinky measurement, it's a faster and easier way to do the test. Slinky Test. Okay, well here we're talking about triaxial accelerometers. I mentioned that in the beginning, but I can do this same type of a Slinky test using triaxial accelerometers and at least a 6-channel. Now most times we don't buy 6 channels, but let's say we have 8 channels, we can use 6 of them with 2 triaxes, do the Slinky test. Much easier to do on a running machine or even, you know, a bigger structure, a piping system, if we want to get the 3D motion. So we can get 3D ODSs from a set of this Slinky data, and we do it by walking the 3 transmissibility chains, one for the X, one for the Y, one for the Z. Very simple, nothing fancy in terms of mathematics, but we end up with a 3D set of, and then we seed it with some cross spectra for the X and for the Y and for the Z. We end up with 3D chain of single reference data with cross spectra FRS or ODS FRS. Same thing if I seed the chain with FRF data, same chain that I've used, just output only data, but I seed it with an FRF with respect to a reference. So I have to go back and make that one measurement on the structure. Now I get a set of FRFs, single reference set of FRFs, and I can curve fit those to get a modal model. So if I use a scaled FRF, what we mean by a modal model is that the mode shapes have been scaled so that we can use them for synthesis and MIMO modeling and so forth. Okay, that's enough of a preamble. Let's get into actually running MEscope, and let me show you some of this stuff. Again, I'm going to open up, I've got 2 projects here. My first one is called 2 moving uniaxial accelerometers. The second one is a Slinky test. So let's just see if we can get through the first one, because there's a lot of details here, but I set this up in MEscope using scripting, and of course scripting uses hotkeys. So every time I define a script, I create a hotkey, and if I press that hotkey, it will execute this script. Now, I'm not going to show you all the details, but we'll look at a couple of them here. Let's go through and run. Let's run the first script. Let me just come up here and show you. I've got 6 hotkeys up here, and they're all numbered. So they're a little hard to see. If I switch this over to a different format here, they become larger. What we call our, let me just show you that. I'm not going to do it, but we'll show that in the options box. If I go to the menu style and I put up a ribbon, the ribbons here, I have to restart MEscope. Right now I'm on a single menu, so I'm going to leave it there, and let's just go out of the dialog box here and hopefully back to what we have. But you can see these have labels on them. The first one is called random responses. So we're going to use some mode shapes, and this is similar to what we did last month, where we start out with some mode shapes. We synthesize some random response of the flat plate here, and then we're going to create from those random responses some transmissibilities and some cross spectra, FRF, and so forth, and we'll end up with a single reference set of data when we're all done. First thing we'll do is create the random response. Second, we'll create the transmissibilities. Third, we'll create some cross spectra. Here's FRFs, calculate FRFs, calculate ODS RF, and then we'll compare shapes. We'll compare the ODS we get from our data with the mode shapes that we started with. So let me just click on this first hotkey, and the hotkey is executing a script. The script has a dialog box in it that's telling us what's going on here. We're animating frequency-based ODSs. Drag the cursor to display a different one, and press the continue button on the lower left down here in MEscope to continue with this process. So I'm going to go ahead and click on OK and do what it's telling me to do here. Well, this is a set of FRFs for this gym beam. So or not the gym beam, but the flat plate. So used to using a gym beam, I repeat that. But if I drag the cursor through this data, these are just a set of 30 FRFs that were taken at the 30 points there. If I turn on the label, you can see the 30 points that are all labeled. There they are. You can see I've made the points a little bigger, and their labels are a little bigger. That's something that you can do with it with any model that you use in MEscope. But this is the first place you want to start with any set of experimental data. Make sure you got some good data, and you can see it looks pretty good. If I display the go back over here and display let me put this cursor back down here and display the real part. There's the real part of the data. There's the imaginary part. Imaginary's maybe got a little error in it. The real part is very clean. And then we can go back to magnitude here and display that. And that's going to be the magnitude and the phase together. So a little bit of complexity. But when I drag this over to a resonance, I get what I recognize as first torsion mode. That's the first flexible mode of this structure. I move to the second one, I get the first bending mode. And by first, I mean it's a simple waveform of the resonance. Get up here to the next peak. Now I got first bending, but in this stiff direction. So that's what we expect from any structure. This could be an airplane wing, a car body, a machine tool, it doesn't matter. We always look for that kind of thing in the data. Anyway, this is just showing us the ODS data by putting a cursor on the FRFs themselves. Let me go ahead now and hit the continue button down here. You can see there's a continue button in the lower left corner, and the script is waiting for me to press the button. So I put the script in the sleep mode. That's a command, a script command, where I can tell it to wait. Now what it's put up here, it's rearranged some windows, and this first one up here is my force input window. So you can say force input at 1Z. So that's going to be over in the corner, 0.1, and there's 10 burst random signals here. Now the burst random is a nice signal to use if you're using a shaker and testing a structure. Here we're simulating it. We created this with the new data block command. Well, I've got to close this out so I can zoom in here and show you what it looks like. But let's just go ahead and look at what else we've got up here. A modal model with 5 residue mode shapes in it. So these are the mode shapes over here in this shape table, and you can see them all. There's 5 frequencies, and below are the mode shapes themselves. We'll look at them in a minute. Over on the left, or on the right, I mean, is an empty data block. So there's nothing in there, but that's where we're going to put the 30 burst random responses of the aluminum plate. And again, it says to proceed, press continue. So let's go ahead and do that. But let's take a little more of a look here at these burst random signals. The whole idea of the burst random is we excite the structure with a random force, but then we turn the signal off before the end of the acquisition time period. And that allows us to, well, we'll see it here in a minute when I hit continue. The structure, depending on the damping of the modes, the damping in the structure, it will ring down. So now when we capture this signal along with the response, we get what's called a leakage-free response. So if we didn't do this, then we'd have to use a Hanning window or something else with this type of an excitation. And then over here, I've labeled it. You can see I've labeled it as 1Z. with a force input. Let me see here, I clicked on the wrong thing, and I want to go down here, and so you can see more clearly how this one measurement, 1Z, pounds of force, and it's an input. So we're going to use MIMO, multiple input, multiple output, together with the mode shapes. Let me put this back. Here's the mode shapes here that we're going to use to synthesize FRS and multiply the FRS by the spectrum of the input and get the spectrum of the 30 outputs. So these are residue mode shapes. They've been scaled. You can see they got units here, a little bit crazy units, but I can use those to model the dynamics, at least over the frequency range of those modes. I'm going to push continue. Okay, so now we've created, using the MIMO output command, created the responses, and now we're going to use these responses to simulate the acquisition of a transmissibility chain. Let me go ahead and push this one. It says transmissibilities. I'm going to move along a little quicker here because we've already used up half of our time. Okay, so here we are. Here's another. We've connected up an acquisition window to the data block with the random responses in it. So this is something that you can do in MEscope. Very handy way to use MEscope and use the acquisition window. Pre-record the data as time records and then post-process them. Import the data into MEscope, post-process them with our acquisition window. So here you can see that the acquisition window is telling me where it's going to make a measurement. Now, I'm going to have to get in and explain more of this to you, but it says press the F6 key to examine 29 measurement sets that will be used in the acquisition window to acquire the data. So what we're going to do here, here's the acquisition window, and it says press the F6 button. Now this window is linked to the model over here, and it's showing me for measurement set number 1. I'll make this larger in a minute so we can see all these measurement sets. Well, let's just do that first. It says measurement set number 1 of 29 measurement sets. So as I push the F6 key, you can see that, let me push F5, you can see measurement set number 1 is going to simply acquire data from the first 2 channels, in this case the first 2 measurements, in the time domain response data block. So we're just acquiring data out of the data block. Then we're going to go and we're going to acquire data from 2 and 3. And you can see over here that 2 is going to be an input, 3 is going to be an output. So this is all set up ahead of time. 3 and 4, input, output. And we're simply going to post-process the data in the ACK window. And up here is our setup for the measurement. We're going to measure a transfer function or an FRF. In this case, because my data is all acquisition data, let's go over accelerometer data, sorry. My data in the data block is all just acceleration in G's. I'm going to measure a transmissibility between channel 1 and channel 2, and so on. My sampling, I'm going to acquire 2,000 samples, and I'm going to do 3 averages. So that's going to be true for each of my measurement sets, and they're all saved in here in the acquisition window. So if I go back here to, let's just go all the way through this thing. Here's all my measurement sets. I want to go back to, there's measurement set number 1. And you can see it's saying measurement set number 1 over 29. The red is my input, and you can see the little DOF up here, 1Z with a colon in front. That's our reference, and the blue is the output. It's at 0.2Z, and then the 1 indicates that's measurement set 1. So then I go to measurement set 2. So I'm just pushing the F6 key here, and you can see. So I've got my whole test set up here for acquiring data on this aluminum plate. Now scripting, again, my scripting is sitting down here waiting for me to push the continue button, and it's going to do all this automatically. So if I push continue button, just watch what happens here. Okay, it's acquiring data, and down here in the lower left, it's actually storing the transmissibilities between a pair of responses. And it's doing 3 averages and then storing it into a data block. So those are the transmissibilities. They're very clean, very little noise, even though we got random responses here. They're completely correlated between each of the pair of responses. So this is a little bit ideal in the sense that in the real world, maybe your responses won't be as cleanly correlated from one point to the next, but they should be, because the whole idea is that the structure is responding with these 5 resonances, but it could be that it's order-based. So you're going to get some ODS FRFs or transmissibilities with order peaks in them. In this case, we get resonance peaks, but we have to be very careful with these transmissibilities because each peak is not evidence of a resonance. Remember, this is a ratio of 2 accelerometers. So you can see the units here, and you can see the DOFs and the measurement set number and so forth is all in here. So as I scroll through these, some of them are very strange looking. That certainly doesn't look like an FRF. That's a transmissibility. Some of them look like FRFs. There's one that's very strange looking, and even a little bit of noise on it here. But what we're going to do is multiply these together in a recursive way, and we're going to seed them with either a cross spectrum or an FRF. And we're going to get a single reference set of data out of this data. See, this is not a single reference set. If you look through here, the reference is changing. You know, 1 and 2 and 3. Every measurement has got a different reference. So we can't use this data to look at ODS. We can't curve fit it. I mean, we've had customers that have called and said, hey, the curve fitter's not working. We find out they took data like this. So you have to be careful. This is not FRF data. So FRF curve fitter is not going to work on this data. Let's go ahead and compute cross spectra. So this is the next hotkey I have up here. Now that I have my transmissibilities, I'm going to seed that chain with a cross spectrum. Now in this case, we're going to calculate a cross spectrum from the original time data using the force input at 1Z and the response at 1Z. And now it's going through and doing the multiplies by the transmissibility chain. And so now it's finished, and it's a scroll through the cross spectra on the right. So they've got a little bit of noise in them. Let's take a look at them here. I'm going to go back here to the beginning one. Now that is the cross spectrum of 1Z with 1Z. So what is that? That's an auto spectrum. How do we know? Well, we can look at the Bode plot, magnitude and phase, and you can see the phase of that cross spectrum is 0 because it's a cross of the accelerometer response with itself. But as I scroll through here, now I'm going to get the second one is a cross spectrum between 2Z and 1Z. And now we got 3Z and 1Z, 4Z. You can see a very clean phase, very noisy magnitude because this is output only data. We only took 3 averages, and if we'd have taken more averages, perhaps it would be cleaner. But again, the averaging would have to be on the seed itself. This is where it started. We seeded the whole transmissibility chain by a recursive multiplication, and this is what we ended up with. All the way down here at the bottom is, but you can see this is a single reference set of data. Let me put that back. Let's go do comparison now, and we're going to do a comparison animation of the ODSs from the cross spectra that we just calculated with the original mode shapes. And what I've done is I've turned on something called maximum MAC here, and the scripting did this for me automatically. What's a maximum MAC? Well, if I go into the animate command menu down here under compare shapes, you can see maximum MAC is turned on. So what that's doing, as it scrolls through the mode shapes up here on the top, here's my 5 mode shapes, so they're being displayed over here on the left. You can see that in here, residue mode shapes. On the right are the ODSs at the maximum MAC location. So as I scroll to a different mode shape, the display down here moves the ODS cursor to the frequency of the maximum MAC pair. So this is all going on behind the scenes. Maybe you didn't know this. This is a standard feature in MEscope with ODS, and in this case the ODS Pro is needed because we're doing a lot of post-processing here, and then the acquisition window would also be needed. So if you go to the website to rent this for a month, you want to rent ODS Pro plus the acquisition window, and you could repeat everything that I'm showing you here. Now up here is the MAC value between the ODS and the mode shape, and it's a value of 1. So even though the MAC values are, the ODS values are different in magnitude or value, the shape is the same, and that's what MAC is telling us. Now this bar chart here is what we call SDI. This is something in MEscope. It's a standard feature. You may not understand it or have ever used it, but SDI stands for Shape Difference Indicator, and it's actually measuring the difference between the ODS or the amplitude of the ODS and the mode shape, and they're quite different. Even though the shapes are the same, you can see it on the animated picture here. Left is the mode shape, right is the ODS. Now the phases, see, there can be a phase difference. MAC doesn't care about a phase difference. They still lie on the same straight line if I were to plot out the shapes. But, and I could change this if I went, well, we'll come back to this issue, but basically I get the same ODS as the mode shape. I'm going to go back here and press FRS now. Since I have a set of transmissibilities, I can now seed those transmissibilities with an FRF, and I'll get a set of single reference FRFs. So this is now just a different seeding process. You can see it creating the FRFs over here, and the transmissibilities are on the left. I am creating a set of FRFs on the right. Okay, it says look through the FRF. So here we just seeded that same set of data, and here was the seed. We started out by creating an FRF, G's per pound, at the driving point. So that's our driving point. Let's put up the Bodie plot here. You can see very characteristic of a driving point. We got a little bit of noise here due to the fact that we process random data to get that, and that noise, because of our seed, is going to propagate through all of our measurements. You can see there's a little noise here in this FRF because we're multiplying each of the transmissibilities by the seed, and then creating the next FRF, multiplying that by another transmissibility, and so forth. But you can see we get a pretty clean, other than that one little noise part there, and then maybe another one out here, because our seed was a little bit noisy, we get a pretty nice set of FRFs, and I can actually curve fit these if I had the modal option, curve fit these and actually recover the actual mode shapes that we started with. But if I go over here and animate, now what I'm going to animate here is the FRFs. Again, the ODS by just putting a cursor in the FRFs with the mode shapes that I started with. And you can see the same thing here. After post-processing this data in MEscope, we're getting a perfect match of the ODS from the FRFs with the mode shapes. Okay, well, we can do the same thing for ODS FRFs. The difference between a cross-spectrum set of single reference data and an ODS FRF set is that the ODS FRF, the magnitude of the ODS FRF is an auto spectrum of each response. So there I can integrate an ODS FRF and I can get the response of the machine in inches per second rather than in G's. And if I start out with a calibrated seed, then I have a calibrated set of ODS FRFs that can be either in velocity or displacement or in acceleration. Okay, well let's go try out the Slinky. So I'm going to stop this, and again, let me just go back very quickly and review what the Slinky test was all about versus the one we just went through here, where we multiplied. This was a test we just did. Sorry, got the wrong picture. Here's the test we just did, simulated test on the plate by acquiring data a pair at a time and declaring one of the channels as an input, the other as an output, forming the transmissibilities this way. Now we're going to go back and do the same thing, but we're going to set up the acquisition window a little differently so that we do a Slinky test. And as I say, that cuts down the number of moves that I need to do with my sensors, and I keep the two sensors hooked to 2 channels or 6 channels of the analyzer, and I just move along, hopping the one accelerometer over the other. So very simple test to do. Again, don't have to measure the forces. So that makes it a very simple test that I can apply on virtually anything. Okay, I'm going to shut this down and open the Slinky project. So let's go do that. I'm going to close this project. No, I don't want to save it. And let's go get the Slinky. Okay, so here's my Slinky project. And we'll go through the same steps, and the only difference being in this project is I'm going to acquire the data into the acquisition window in a different manner, and then I'm going to invert some of the transmissibilities using the property of inversion so that I end up with a set that I can go ahead and seed with an auto spectrum or an FRF and get a single reference set of data. So that's the whole idea here. Okay, so here we are. We're starting off the same way as we did before. We've got a set of FRFs, and we're simply showing that we got a good set of data to start with, and then what we've already done, we're not showing it here, is we've curve fit these FRFs to get a set of mode shapes. So we've already done that. Let's go ahead and continue. Okay, so we use the mode shapes to, in MIMO, to calculate some outputs due to a random input at 1Z, a burst random input. with 10 burst random sets of data, and each of those, we didn't look at those, but this is a lot of data in here. Let me just we'll take another look. It's the same set of data we used before. Let's go look at the block size. Okay, it's 20,000 samples of data. So this is a lot of data that we created with the new data block command, and but we're going to process it in 10 averages. So we're going to take 2,000 samples at a time from the time record, but then in the ACK window, once we do the FFT, we get 1,000 samples in the frequency domain. So that's just standard signal processing. And so let's just go ahead and do that like we did last time. So this is, we've calculated the 10 responses for the 30 points on this, on the, let me just drag through here and show you. Here's all the different responses at the 30 points on the plate due to the random excitation. So this is simulating a burst random shaker test, if you will. All right, let's go ahead and hit the continue button. Where is it? Let's see. Oh, I guess we just finished. There's no continue button here. Now we're going to compute the transmissibilities. Same thing we did last time. However, you will see the difference here in a minute as I bring these up. Connected up. This is telling me basically the same thing. Use the F6 key to look at your data. I'm not seeing what I was hoping to see here. Oh boy. Well, here are my, I'm not seeing the little arrows on the picture here. Let me just show you what the data is set up as in my acquisition window. Let's go all the way back here to measurement set 1. Measurement set 1 is the same. It's going to be input. Channel 1 is input, channel 2 is output. Now let's go to the second one. See, they reverse. Now channel 2 is output, channel 2 is channel 1 is or channel 3 is input. That's where we did the Slinky. And for some reason it's not displaying it, but you can see the Slinky is hopping. It's reversing the process as I go through the measurement sets. All right, let's just go on. We're kind of running out of time here. I'm going to go ahead and process the data. So what we're doing here is we're calculating the transmissibility, same way we did last time. You can see down here I'm averaging. It's going along, the cursor showing me the 3 averages of the time responses. Now it's not scrolling through. It's actually taking different data each time it makes a measurement. Over in the lower left here are the transmissibilities. Again, a ratio of the accelerometers, but taken in a different order this time. So with Slinky, we've got to post-process this data and invert essentially every other one so that we get a usable set of transmissibilities. It's not putting the arrows up like we did the first time. There's a little bug in the software. We've actually seen that and fixed it. Let me go ahead though and calculate. Now the next hot button I have here says calculate the cross spectra. So before we can do that though, here it is reversing all the Slinkies, every other one. So, or not reversing but inverting. So here is the ones that we actually acquired on the left, and then the inverted ones, this data block over here, we went through and inverted each every other one. And then it says to proceed, press the continue button. So let's go ahead and take this set of Slinky, corrected Slinkies now, and we're going to compute cross spectra. On the left are the converted or the inverted Slinkies, and on the right we have a new set of cross spectra, basically the same as last time. Let me go ahead and do the animation. And so what we're comparing here are the original mode shapes with the cross spectra that we calculated in the Slinky process. So with that, I'm going to finish up my presentation. Mark, do we have any questions?
Yeah, we do have one question that came in. It says, is Hertz a type on the x-axis for the time waveform? I think he was referencing one of your time waveform graphs where you had Hertz in the x-axis. Really? Yeah.
Okay, well, let's go back, and that could be a bug. Hertz is never.
I know.
I'm going to go back and push this first button here, and we'll get the time records back. And we definitely have bugs in our software. We acknowledge that. So let's go back and see. Okay, yeah, it says Hertz, doesn't it?
It's a good catch.
That is the bug in the software, but you can see that.
Yeah, definitely a bad label there.
Yeah, and that came out of the new data block command. Here, let me do this. Let me just. I'll go in here in MEscope, and we'll see if it corrects itself. I'm going to FFT. There is the spectrum of that signal. Again, we had 20,000 samples in there. So, and now let's go back in the other direction with the inverse. We can do this all day long. FFT, inverse FFT, we never lose any information. There it is. So, good catch.
Yes.
That is seconds. Down here we've got seconds in this empty data block. If I go ahead and press this continue button down here, you can see that we get time records. So yeah, I don't know how that got in there. That's a bug, and but we corrected it by just doing the FFT and the inverse FFT. Good. Well, somebody was paying attention. Anyway, to summarize what we did here today, let me just put the slides back up, and we're going to have a technical paper on this, and we haven't done all that yet. But what we did is we did 2 different tests simulated with a random excitation. Now, we could have done it with a impact. I think next month in the webinar, I'll do a simulated impact. We can do that to an MEscope, get the impulse responses, post-process that data to get FRFs, or we could just use the output only and compute cross spectra, ODS, FRFs, using this what we call transmissibility chain measurement.
Hey, while you're on that, I got another question that just popped in here. It
Good.
Says, using the chain method, will the quality of the final calculated single reference model be corrupted by a single poor quality? I'm thinking I'm guessing what he's asking, if you have one bad measurement along the chain, will that corrupt all of your data, since they're all sort of
now, I explained a little of that in the beginning when I started out with a bad seed. That error propagated all the way through because we're doing multiply, multiply, multiply. Now, you could minimize some of that. I mean, the chain that we formed, actually, here it was with the FRF, we started at the beginning of the chain, up here at point, actually 1, 1. we started with a driving point FRF at 1.1, and then we multiplied all the way down the chain 30 times. So the answer to the question is absolutely right. If there's error in the chain, it's going to propagate, because you can see the recursive calculations are going on here. However, if I made a bad measurement and did a single reference test, that's bad data also. This could, in fact, cause more errors in depending on where I seated the chain. So this example here, we're seating the chain in the middle, and we're walking in two directions. One is from the middle to the beginning, and the other is from the middle to the end. So that would be a way to minimize errors caused by your seed measurement. But in fact, yes, if you made one bad measurement as you're going along, either with Slinky or with the chain measurement, it's going to propagate. But bad measurements are bad measurements. You want to do the best job you can. And the whole idea here is that it's easier to take the data. And if you're testing a long pipe system or a paper mill or something, and you don't, the nuisance of having to run a long wire is what we're overcoming here. Okay. Anything else?
No more questions.
Good question. We appreciate good questions. Again, that tells me that some of you are paying attention.
If you have additional questions that we didn't get to, please feel free to email us, again, at webinar@vibetech.com. And,
I can send you these projects too. If you are an MEscope owner and you have at least an ODS Pro package or something higher, a Modal package or Modal Pro, then you could run these scripts, press the hotkeys, and go through it yourself and understand a little more of the details. Now, we didn't get into all the scripting. The scripting is pretty simple to do this. We're just calling MEscope commands and doing things. I set up a couple of loops to do the multiplies in a loop. So it's very simple code to do this sort of a post-processing. Now, we are going to build some of this into MEscope. We'll probably build a transmissibility chain command in so that you can post-process your chain. And you don't have to do it the way it was done here. You can just imagine there's different ways to do this. Well, the Slinky test is kind of hopping over one another with two accelerometers, but you could leave one fixed and then just move the other one along for a while until the wire gets, your wire isn't long enough to go any further, and take all those measurements and then move to another location along the structure. Let's say it's a piping system, and then take another sequence of transmissibilities. You could do it that way, or you could simply measure transfer functions with an impact hammer directly, or cross spectra directly. We could do all this with cross spectra. We don't need to form the transmissibilities. The information is in the cross and auto spectra of the and that's all the ACK window does, is it takes the cross and auto spectra and does the divide operation and gives you the ratio of the two sensor signals. So a lot of ways to skin the cat here.
Hey, we got one more question that just popped in here. Let me go see if we can get an answer here. We got. Let me see if I can understand the question here. During data acquisition, if generating transmissibility with analyzer software, I assume we have to change reference channel for each measurement using Slinky method.
That's correct. You'd have to be careful. Well, no. See, Slinky, if you're using, let's say, a two-channel analyzer, right, and
that is your reference.
Channel 1 is always your input or your reference. Channel 2 is always your output or your roving. So you don't need to change anything in the analyzer. You simply take channel 1 and hop over channel 2, and now that's still channel 1 that's still your input or your reference. Channel 2 is still your output or your what we call roving. So no, you don't need to change anything in the analyzer. You simply need to label your measurements correctly, with the degrees of freedom of the. See what we've done here. We post-process knowing that we use the Slinky method, so every other transmissibility needed to be inverted. But if you label the measurements with the correct input and or with the correct degrees of freedom, when we build this into MEscope as a post-processing command, as long as your degrees of freedom are labeled correctly, then we can do all the math inside of MEscope and come up with a single reference set of data. Our current ODS FRF command allows you to import a set of transmissibilities, but it requires that they all be with respect to a single reference. And then we simply go through and we take the auto spectrum of that reference, take the square root of it so we get true motion, and we multiply that by all your transmissibilities, and that's how we form an ODS FRF. Or if you give MEscope your cross spectra and auto spectra, then we do the calculations in MEscope to form the transmissibilities, multiplied by the reference, and give you a set of ODS FRFs that way. Or you can give it time records. You can just acquire the time records with your acquisition system, import those into MEscope, and that's the way we process the data here with the ACK window. However, you can just post-process with the ODS FRF command in the data block window. You can process the time records the same way. Let me just show that to you real quickly. I'm going to go over here and say transform ODS FRFs. So here's the current command in MEscope. So I can give it, see it's already said, well, you're executing out of a data block with time waveforms, and it also sees that there's some other time waveforms, the responses. So I could just pick, this one here and this one over here. But you can see the other options here that are available: auto and cross, spectra, and transmissibilities, and reference auto spectrum. And then, of course, when I give it time records, I can actually compute these auto and cross with this command also. So 3 different ways to do it with the current software, but each one of those is assuming that you have a single reference set of data. I'm doing the post-processing. Good question, though.
All right, let's go ahead and wrap it up.
Let's wrap it up.
We are recording this, so we'll get this posted out to the Vibrant Technology YouTube page here in a couple days. So take a look at that if you want to go back and review any of this webinar.
All right. We'll talk to you next month then.
All right. Thank you, everybody. We'll talk to you all later.
All right. Bye.